Well, that was a great way to get started. One of the things I love most about computer science is the research that we do is so often, as Kristen has illustrated so nicely, at this nice sweet spot, the intersection of what's impactful, what's challenging, and what's fun. Our next speaker is a distinguished alum of our department, having received her PhD here in 1998. Today she's the Deputy Chief Technologist at JPL's Mission Systems and Operations Division. And I think we can all agree that she wins the award for the most fun title for a talk today. And her title is Firing a Laser on Mars Using Artificial Intelligence. Dr. Tara Estlin. Where's Tara? There she is.
Hi, everyone. So, I'm Tara Estlin, and as you just heard, I'm a graduate of the department. I came to the University of Texas because it had not only one of the best computer science departments in the country, but one of the best departments in artificial intelligence, which is what I wanted to specialize in. I then went on to work at the NASA Jet Propulsion Lab, looking at how AI can try and help further space exploration. I'm going to tell you a little bit about some of that work. So first, just a little bit about JPL. So JPL's charter with NASA is to manage unmanned robotic spacecraft to explore the solar system. So we currently have 17 spacecraft and an additional 5 instruments that are in different parts across the solar system. And one of our main focuses over the last 15 years has been exploring the surface of Mars. So we've sent 3 different Mars Rover missions, and we have another one going in about 4 years. The first one, which landed in 1999, flew the Sojourner rover, and you can see a replica of her there on the lower left. So Sojourner was rather small. She's about this big. I could actually pick her up, walk around. She was built to last around a month. It ended up lasting around 3 months, and at the time we thought that was wildly successful. We then sent another 2 rovers that landed in 1999. It landed in 2004. Those were Spirit and Opportunity, and you can see a replica of one of those in kind of the middle left. So they're bigger than Spirit, more around the size of a golf cart, had a much more larger suite of instruments, much more driving capability. They were built to last at least 3 months, though we hoped they would last longer, and we definitely got our wish there. Spirit lasted 6 years before we lost her, and Opportunity, 12 years later, is still going strong, and we drive her almost every day. And then 4 years ago, we sent our latest rover mission, which landed Curiosity. So that's the very large rover you see there on the right. So Curiosity is around the size of a small car. She weighs 2,000 pounds and is by far the most sophisticated spacecraft we've ever landed on another planet. A whole new suite of instruments, and one of the best things about her is that she can actually go up to a rock with the arm and core out a sample of the rock and put it in an inside laboratory, break it down, and figure out exactly what the rock is made of. Now combined, these rovers have driven miles across the surface, and Opportunity and Curiosity show no signs of stopping anytime soon. Now, just real quick, you may have wondered, okay, we've been there for a while. What have the rovers actually found? They've actually found a number of significant scientific discoveries. I listed a couple here. Of course, one of our main goals, so not the only goal, is to look for evidence of current or past life. And one of the requirements for life is water. So we spent a lot of time looking for water, and we've actually found conclusive evidence of water on a lot of different areas of Mars. And this includes not only finding old spots of water, but actually finding evidence of ancient lakes and stream beds where we think water would have actually been drinkable or fresh water. Now, that's one building block of life that you need. Another important building block are organic compounds, or compounds that contain carbon. This is another requirement for life. So that's been a main goal of Curiosity. That's one of the main reasons that we sent this onboard laboratory. And we have found organics, and we found other chemical properties that would be required for life to happen. So at this point, we found all of the building blocks. We just haven't found yet the direct evidence, but we think that will be the next step. And then third, just another interesting discovery, is we found evidence of present and active methane in the Mars atmosphere. And you may say, well, why is that a big deal? Well, it's actually rather interesting. We've not only found methane, but we found that it's dramatically changing. In one 2-month period, we saw that it actually increased twofold in the atmosphere. And this means something is producing it. And one of the big ways you produce methane is actually living organisms. It's not the only way, but it is one of the ways. So that's going to definitely be something we keep looking into. Now, one of the reasons to use AI on the rovers is to make them easier to operate and to make them be able to explore farther on their own. Now, there are a number of challenges of operating the rovers. One is we have very limited communication. We have a lot of spacecraft. We only have a handful of antennas that could actually talk to deep space spacecraft. So you're only talking to them infrequently, often just once a day. The rovers have a lot of instruments on board. They all have different operating constraints, acquire different types of data, need to be run in different ways. And one very important thing is safety is a priority. So you have an incredibly valuable spacecraft on another planet. You have no Martian pit crew that can come and fix the spacecraft if something happens to it. So you want to be extremely careful. Of course, you want to explore as far as you can, but you want to minimize risk as much as you can. One of the ways we do that is almost all of the activities for the rovers are planned by human operators. We send them a set of instructions every day, but that's gone over by multiple people to make sure nothing unexpected is going to happen or we're as safe as we can be. And that's great, but it also really slows things down. So it means if you want to take science observations in a certain area, the rover has to stay put for several days. And the reason is it gets into a new area, it takes images of its surrounding terrain, it downlinks those to Earth. That takes time. Folks on the ground have to look at those images, pick out spots that they want to take science measurements, like the rocks I've shown up there. They then have to put together a set of instructions to take those measurements, uplink them back to the spacecraft, and have them executed. And at this point, the rovers had to sit there for a couple days. So one of the things we're looking at is how do we collect data from more locations, but not make the rovers stop for days at all of those locations. And this is where AI comes in. So one of the ways we did this is we developed a system called Aegis, which stands for Autonomous Exploration for Gathering Increased Science. And it's basically a new way for the rovers to autonomously collect science data. Aegis provides what we call intelligent targeting and data acquisition capabilities. So as soon as a rover gets into a new area, it can take images. Those are analyzed on board by the Aegis software. It then looks for high priority science targets such as rocks or other terrain features. And if it sees something that it believes the scientists will be interested in back home, it goes ahead and takes data on those features. It can do this all without talking to anyone on the ground. It's currently operational on both Curiosity and Opportunity. And I don't have a lot of time to get into the details of it, but just to give you a little flavor, basically it's using an onboard computer vision technique. It's using different forms of edge detection to find suitable targets. So it was built as a rock finder. You see an example of it finding a target down there at the bottom of the slide. It's basically looking for edges or intensity gradients in the image, and it's looking for edges that it can fully enclose or draw a contour around. Once it picks out a set of targets in the image, it then evaluates different properties. What is their color, intensity, shape, size? And looking at those properties, it then determines what would be interesting to scientists and goes ahead and collects some additional data on its top targets. That data can be collected with different instruments. It could be collected with high-resolution cameras, or it could be collected with spectrometers, which is an instrument scientists use to basically determine different mineralogical and chemical properties about the terrain. Now, I'm mainly going to talk about its use on Curiosity. So on Curiosity, we're using it with a spectrometer called ChemCam. ChemCam is what's known as a laser-induced breakdown spectrometer. It basically fires a laser at a location up to 7-8 meters away and vaporizes a small portion of rock. And as that vaporization happens, it collects the light spectrum that comes off of it. And using that, it can tell the different elemental composition of the rock. Now, before, when you took ChemCam measurements, it took 1 to several days. Now, with Aegis, you can do it in a matter of minutes, and then the rover can drive on. Now, there are two ways we're being used with ChemCam. One is analyzing wide-angle images. So an example of that is on the left. This is a Curiosity navigation camera image, or what we call a NavCam image. It's used to both navigate the rover and for science purposes, and it shows a good swath of terrain. So there you're seeing a field of view of around 9 to 10 meters across. And in these images, we're usually looking for rocks. In this example, we were looking for some dark boulders out there, and you see the top 5 targets that it picked for ChemCam measurement. And then on the right is kind of an example at the other end of the spectrum. So this is a more microscopic image. So all of these instruments are basically on the rover mast, but we do have a microscopic imager there. And instead of seeing meters of the terrain, it sees more centimeters of the terrain. So that image you see there is around 15 centimeters across. And the nice thing about this imager is you can see really fine properties of the terrain. And one thing the scientists love to see are veins in the terrain. And so you can see that vein there. And basically, this is usually, a vein is usually created by a past water flow that has deposited some sort of mineral in a crevice of a rock. So they love to look at these. It tells them a lot about the history of the planet. And so another application we have is picking out different spots on the vein to hit with the laser. Now this just steps through how it works on board for the 2 missions that we're working on. So Opportunity is MER, that's Mars Exploration Rover, and Curiosity is MSL, Mars Science Laboratory. And the process works like this. It's rather straightforward. You acquire an image of the terrain, either a NavCam or one of your remote micro images. Aegis then detects targets in that image. Here you see it picking out a series of rocks. It then extracts a series of properties on those rocks. Again, their size, their shape, their distance, their color, the texture of their surface. And using that information, it can then filter out certain targets. Often you want to filter out small targets or targets that are too far away from the rover. And then it can also use those properties to prioritize targets. For instance, maybe you're looking for a larger, lighter colored rock that has a smooth surface. Once it prioritizes, it then sees if it has any really nice targets, and if so, it picks a center point on those targets to center the laser, and then it acquires a laser measurement. It can just acquire one spot, but usually with the laser, you acquire a whole series of spots, so you get multiple data on that rock, and then it can repeat it for multiple targets. Now here are just a few examples that we've done recently on the surface and the different targets that it took. So lately we've been seeing a lot of bedrock or outcrop. Now this might not be exciting to your eye, but it's very exciting to a planetary geologist because again it's a great way to tell information about the history of the surface. So these are different targets that the software picked out. Here's a nice example where they were looking for bedrock, so it was able to distinguish between the embedded rock and the more loose rock on the soil, which they weren't as interested in this terrain. And here it found a piece of bedrock that had broken off and was kind of standing off on its own. And then just a few more examples of rocks it's found recently. Then a few examples on more the micro image. So here's a very common thing you see. It's not as much a vein as what they call white concretions, but still a former mineral deposit. So picking out another large spot on a vein and a few other smaller spots on the vein. So that's exactly what we wanted to do. Now, I wanted to mention a few of the challenges of doing this on board a spacecraft. Of course, one challenge is you want the software to do the right thing. You want it to pick out things that the scientists are interested in. All of these instruments only have a limited life. They can only take so many measurements. So you want to make sure that you're using them in the best way possible. But we also have a number of other challenges, many of I think that are rather unique to using AI on spacecraft. So one is we're using them on very complex vehicles, both hardware and software-wise. So Curiosity has 10 different instruments and a whole suite of cameras on board. It has a separate mobility system, thermal system, power system, communication system, and all these things have to be coordinated. Often when you're putting software on the rover, you have to use a number of those subsystems. You want to make sure you don't do anything untoward, you don't cause any problems, you don't write over anyone's data, you don't use too much memory. You don't want anything to go wrong. Because again, if something goes wrong, it can be very difficult to recover. Also, the particular instrument we're using Aegis with, this ChemCam laser, has its own series of safety constraints. For one, as you can imagine, when you're taking images around the rover, sometimes if you're pointing down to the side, you get a little bit of the rover in the image. maybe the wheel, maybe a little bit of the arm. So you want to be very careful not to laser the rover itself. That would be rather a bad thing. ChemCam also is very sensitive to the sun. If you point it anywhere near the sun, it will actually fry the optics. So you want to be very careful about that. And when the sun's high in the sky, that's not a big problem. But early in the day or later in the day, and we do take measurements throughout the day, it is possible to get it near the sun. So you want to be careful about things like that. And then one other challenge we have, I think that's really unique to us, is that we're building these spacecraft and this hardware to operate in a high radiation environment. So Mars has a lot of radiation. There are other planets that are even worse, but Mars definitely has enough to cause problems. And if you send a regular computer to Mars, you will see a lot of problems. First, you'll start to see some random bit flips, some random resets, and eventually it's going to die. So basically, we have to send radiation-proof computing equipment. So it's radiation hardened, so it can survive for a really long time in a high radiation environment, which is great. But unfortunately, the radiation hardened processors are usually several generations back. They have to be extremely proven processors, and so they're basically orders of magnitude slower than what you have on your desktop. And they're actually significantly slower than your cell phone processor, and I should say they're significantly slower than your cell phone processor a decade ago. Now, they are improving slowly but surely. And of course, we also are picking these processors often 5 to 10 years before the mission even flies. But it's a slow process. So you're working on a very slow processor on Curiosity. It's 133 megahertz. So this means you want to do great stuff with software, but it has to be extremely efficient. It has to run fast. It has to use only a small amount of memory. So this does make things challenging. But I have been really impressed with what we've been able to do. Now, I thought I'd just leave you with a little preview to the next rover mission. So in 2020, we're sending the next rover, and this is going to be the first stage of Mars sample return. So there's an illustration of the rover there on the right. Structurally, it's very similar to Curiosity. However, it has an entire different set of instruments, new and improved. And there will be a new laser spectrometer, which you see down there at the right. Instead of ChemCam, it's called SuperCam. And it can take even more measurements from a farther away distance and collect more data. And again, this is the first stage of Mars sample return. So the main job of this rover, will be to go around to different spots on the terrain and collect different rock samples. So it actually choose different rocks. It's going to put them in an onboard cache. And then at the end of the mission, it's going to store that cache. And then a later mission will go pick that cache up, blast it off the surface of Mars, and bring it back to Earth. And here's where we think we can definitively tell whether life existed on Mars, because we're going to have now a lot of rock samples from Mars on Earth that we can look at our own laboratory. And then one last thing I'll mention, which is kind of a neat thing about this mission, is we're sending something we've never done before. We're sending a Mars helicopter, which you see an illustration of there. So that's going to go with the Curiosity rover. It'll be able to fly off to the side and get us a perspective on the surface of Mars that we've never been able to get before. So that'll be pretty neat. And with that, I'll close. I'll leave you with a selfie that Curiosity took of herself. She actually has a camera on the end of her arm, and she can look at herself and take pictures, so we tend to do that periodically. If you have any questions or interest, please feel free to email me or check out the following websites. Thank you. Oh, sure. Yeah. Yes, it's based off the IBM PowerPC. And that's also the original, an older version of the PowerPC is what flew on Spirit and Opportunity, which was even slower. I believe 16 megahertz on that one. Yeah. Oh, definitely. Yeah, so I mean, I would love to do everything like that, right, if it were up to me. But we move in kind of baby steps, if you will, sometimes with these missions. But yes, we already have kind of new and improved versions of the software that would be able to learn from its environment. not only be able to move around to like get different perspectives, as well as using more of a machine learning approach where you would kind of learn as you go. And those all are things we're looking at for 2020. We probably won't be able to do everything I want to do, but I think we'll be able to do a lot more. Yeah. Oh, that's a good question. I'm not even sure I know the answer. They change it all the time. And it's funny, I kind of combined it into 2 missions, but it's actually 3. So there's going and collecting the rocks and caching them. There's a mission that will go and blast it off the surface, and then it'll go into orbit. And then there's a 3rd mission that will actually go collect it from orbit and bring it back. Now, we only have a launch window to Mars every around 2 years, and that's when the planets are kind of aligned where we can get there in only about 8 months. So they have to be at least 2 years apart, but it'll probably be more like 4 years apart just to get the missions together. So I'm guessing we're talking 2028 for the one that will actually bring it back. So, yeah. That's a great question. I've not worked on the helicopter itself, but I can take a guess. I mean, the atmosphere is much thinner on Mars, so I think that will be a difference. And then the gravity is about 1/3 of what it is on Earth, so that'll be a difference. And that actually does kind of create some challenges for testing, even the rovers, because you're using them in a very different gravity environment. Yeah, back in the back. Right now, the data just comes down to the ground and they look at it at the ground, but that is something that we've talked to them about and they are interested in, is you could easily run an algorithm on board to see exactly what what the data contains. And as you can imagine, if you're taking data of something that you've seen before, maybe you're not as interested in, but if it's something new, you might want to take a lot of additional data and decide that right there. So that's something else we are talking to the missions about, and maybe it'll happen for 2020. Yeah. I'm sorry, I didn't catch that. Can you say it a little louder? Not that I'm aware of, but it would probably be a better question for our science team. I'm just a lowly engineer, so. Yeah. I do not know what the power system is for the helicopter. The Rovers, it's an RTG, so it's a nuclear power source for Curiosity. Though Spirit and Opportunity were solar powered, so there is some possibility it's solar powered as well. And also, it's not expected to last as long as a rover. Since it's our first time doing it, it might just last on the order of a few months. So I think the power system can be very different. But it's a good question. Now I'm curious. I'll have to go look it up. Yeah.
Are you planning on having 2 or more rovers operating in conjunction with each other?
That would be great. Another great AI problem, I think. So no, not right now. Though it has been talked about, we want to go to different spots on the planet, and that tends to drive things. So even though Spirit and Opportunity flew together, they actually went to very different spots on the planet. And it's funny, one of the reasons we sent 2 rovers there was actually a risk reduction. We were landing them in a newer fashion. Spirit Opportunity, basically, when they landed during descent, it puffed out this big kind of parachute material and made a cocoon, and then they bounced as they landed. And there was a danger that if they hit a rock in the wrong way, it could have been mission ending. So we sent 2 just in case, and then they both landed great. But that didn't really answer your question. It would be great to send rovers that are close together. That's always talked about. But right now, the drive to go to different spots is too big. Yeah?
You mentioned that the range of the laser was 70 meters, is that right?
7 to 8 meters, actually. Yeah. Yeah, sorry about that. Yeah, no, it's 7 to 8 meters. The idea is the rover gets into a new area partly since we have this laboratory on board, you want to take samples of rocks, but you can only do that of so many rocks. It takes a long time to get the arm on something, get a core sample, and bring it in. And what ChemCam lets you do is like test a bunch of different spots, get an idea of their elemental like composition, and then you can choose what of those spots you want to core. But yeah, it only goes to 7, 8 meters. I think the next one will go a little farther, maybe to 10 to 11 meters.
Well, I would say, I suppose that the limit there is actually the range of the spectrometer detection.
Yes, that's correct. Yeah.
Do you use LiDAR?
We do not use LiDAR. My recollection is LiDAR is fairly power intensive, and we have to be very, very low power, if you will. Even though we did this time fly a nuclear power source, our overall, and I'm forgetting what our overall power budget is, it's still very small per day. It'll last a long time, but we don't have a huge amount of power. So, yeah. Let's see. Well, I think most people would say it's a discovery of organics. And though that's probably doesn't sound as interesting to you or me, that was a big find. So we've known about water for a while. We wanted to find more sources. But finding organics, I think, was a big thing. I think my favorite find, which is not necessarily the most interesting, was on the Spirit and Opportunity rovers, which I worked on for a long time. And Spirit had actually lost a wheel at a certain point in time. One of the drive motors stopped working. But we were able to still drive her, just a lot slower. And we actually kind of had to drag the wheel as we drove. But as we were driving, we dragged the wheel through some material that churned up this white substance, which ended up being one of the best finds of water that those rovers found. And we would never found that if we hadn't lost that wheel. So I thought that was kind of cool. So, was there, okay, yeah.
Yeah, are you able to actually make some improvements to the algorithm or adjust things as the mission goes on, or is it essentially static?
So you can make improvements, but it's a very long process. They're very careful about what gets uploaded. Even a small, say, bug fix or change in the software has to go through a whole series of testing. So we basically have a full replica on Earth that we test everything with. And it's usually, you're talking a 6 months process, maybe longer, depending on what you're testing. And a lot of it is, even if you've shown your algorithm can work, again, a lot of it is making sure it's not going to do anything to put the vehicle in a bad state, right? That's the majority of the testing. So you can do it, but it's a big investment. So you can't do it very often. But we have made upgrades before. I mean, this software actually was not there when we landed. It actually went up a year or two later, if you will. So it was one of the upgrades that they made. Okay.